In this short video, we're going to look at decarboxylations, but we're going to start with a carboxylation. Here's an old reaction that you should have learned last semester. You take a lithium reagent and you attack carbon dioxide. What do you get? Well, you get a carboxylate, and of course that carboxylate can be protonated to give a carboxylic acid. It's a good synthesis of carboxylic acids. But what about the reverse reaction? Now, what do I mean by the reverse reaction? Could you start with a carboxylate and go back to the anion from which you started, which of course would be this you start off with this lithium compound. So would this work? You could draw some arrows to show it working. You simply would bring those electrons from the O- back, form the double bond, and kick out, well, this anion. You kick out a carbanion. Now, is this going to work? Looks pretty weird to me. No, it is not going to work. Yes or no? No, it's not going to work, because a simple carbanion is a terrible leaving group. You gain some energy from the carbon dioxide, but no way are you going to kick out an anion like a simple carbanion. It's simply not going to happen. So forget it. Not going to happen. So let's do another one. Here's an LDA reacting with this ketone, and you know it gives this nice enolate. What you may not know, because we haven't talked about it yet, is that enolates will also react to carbon dioxide, just like a simple lithium reagent. So here our enolate reacts with carboxylic acid, with carbon dioxide to give a carboxylate, which can be protonated to a carboxylic acid. Very similar type of chemistry, and again we get a nice carboxylic acid. Now, what about the reverse of this reaction? It looks like we still have to kick out a carbon anion, but what happens here? Well, draw some arrows. Here we go. Draw some arrows. You heat it up. What happens? You bring in the electrons from the O- again, forming the double bond, which will give you your carbon dioxide. That kicks out this carbon here, which of course is now an enolate. This actually looks pretty good. This is a pretty stable thing. It's the same enolate that we started with up here, and those enolates are, they don't have bad stability, and we gain the energy from the released CO2. CO2 is a stable molecule, and of course we get an entropy kick as well, because we're kicking out this gaseous molecule. Same thing happens if you protonate it and you heat up the enol. You get this beautiful cyclic set of arrows where the OH electrons come down, forming the carbon oxygen double bond of the CO2. You use the carbon-carbon bond electrons to form your enolate, and the carbon-oxygen double bond electrons go up there and grab the proton. So this also works very well, but the product is actually now an enol, and of course this enol will go ahead and tautomerize to the ketone. So the enolate and the enol are both decent leaving groups, and so these reactions work quite well. Now, what do you need to do this reaction? Well, what you need is you need your carboxylic acid group to be beta to another carbonyl. And indeed, the secret of all these things is looking for that beta-carbonyl. So if you have carboxylic acid where the beta carbon contains another carbonyl, you can do this reaction. It works really nicely because you get these nice stable leaving groups. So enolates and enols are okay leaving groups. Now, okay, what I want you to do is pause this video. Pause it. You're not pausing it. You're still standing there. Pause the video and work problem 1. This is problem 1 down below. When you're done, you can unpause and look at it again. I'm not going to go till you pause and do it. You did it? Okay, you did it. Let's look at the answer. So what's going to happen? Well, first thing to do in drawing these things is redraw the molecule so the OH is up in the air pointing over toward the carbonyl. This is a realistic way to draw this molecule in the first place because it gives you this nice hydrogen bond. And indeed, in this mechanism, essentially what happens is the hydrogen is going to jump over to this other carbonyl as the reaction proceeds, and you're going to kick out your CO2, and then of course your enol is going to tautomerize to the ketone. So that's pretty good. So all right, you did that one. Does this look like your answer down below? Oh, you didn't do it. Ah, you didn't pause. Okay, all right. Well, let's try another one. Okay, pause again. This is problem 2. Better do it. Okay. I'm going to give you a little bit of time. I know you're not pausing. Okay, I give up. So again, what are you going to do? Well, again, redraw draw your cyclic set of 3 arrows. This is the decarboxylation. You kick out your CO2. In this case, you get something which is looks a little bit weird. This is essentially the enol of a carboxylic acid. Now these enols are not stable at all, so this is going to very, very quickly to automerize to the carboxylic acid. So this is a less stable enol than normal, but indeed this reaction still proceeds. So this up here is malonic acid with an ethyl group in the middle, and it's going to be an important molecule as we go on. Let's do one more decarboxylation. This is one we actually did before when we talked about protecting groups. So this is a carbamate, and carbamates, of course, will also decompose to give carbon dioxide. They go by a little bit different mechanism, of course, because there's no beta-carbonyl. But what do? You protonate that nitrogen of this carbamate. Then you essentially, the whole thing essentially falls apart as you grab the proton off the carboxylic acid portion of the carbamate. And this just leads you directly to carbon dioxide, hydronium ion, and amine. And of course, that amine would grab the proton off the hydronium ion. And there you go. So again, you decompose to give carbon dioxide. So these decarboxylation reactions are very important. They're very important in biology. In fact, the release of CO2 in organisms is often occurs in a reaction very much like these, and it's often an important energy boost. So these are important things to recognize. Thank you.